Okay, great. Before we start, let me show you something. So maybe I'll go here. Um, so there's a link, and let me type it in chat as well. So if you want to type it out yourself, it's scheme review dash code. If you'd like to, so I guess you can choose your own way of following along and solving the problems. But one way that I think a lot of people like doing that I didn't know of until recently is that people like to go to like code.1618.org and like actually solve the problems in the editor. So if you'd like to do this, we made some skeleton code and some kind of primitive doc tests for you to use. So if you go to this link, you'll find yourself at this file in Drive. Just click download. I promise it's not suspicious. And then you can open it. Oh, choose application. And then once you open it, you should see a big file. It has first all of the problems that we'll have on this review, and then it has a bunch of doc tests at the bottom that are all commented out. If you just copy the whole file, then you can go to code.cs1618.org/scheme. Wait for it. If you click new here, it'll make a new scheme file. You can paste this in. And I don't know why mine always pastes twice. Maybe that's a glitch in the scheme editor. But you can end up with something like this, where you have every single problem here, and then you have test zone. And once you complete each of these problems, for example, maybe I write some solutions. Maybe I just define it like this. That's a function, and I wrote one of them. Now, what I can do is I can go to this tests. Notice this one is digit prod. You can kind of tell just by whatever is in the test. You can highlight all of it, uncomment it. But to uncomment and comment, you can press, I don't know how you can do that on most platforms. What I do is I use command slash. I think maybe control slash works on Windows. If you know how you can block, uncomment, or comment things in your editor, that's probably the same shortcut. I'm not quite sure. Otherwise, you can also just, like delete these. Anyways, then once you solve the problem, you think you've solved it, you can run it. And seems like there's some unexpected tokens somewhere. I suspect this may be, let me check this out. I think that's, oops. You may have made a mistake. I think you might delete a parenthesis here. Let's try now. That's not good. Okay, so maybe the doc tests don't work for now. If someone figures it out, then great. Otherwise, you can just use this to write the code in. Dang, that's a bummer. Okay, cool. Let's go ahead and get started. Let me share the slides. Today we are talking about scheme. I'm glad to see that a lot of people showed up. If someone wants to link the slides as well. Yeah, there's another file for the solutions if you'd like to look at those. Okay, so I know we call this review session scheme, but I'd like to center this around kind of the idea of lists, because when we work with scheme, a lot of what we're doing is working with lists. So let's start off with a reminder about what are how do lists work in scheme? So we learned about two types of lists in this class. We learned about regular Python lists, and we also learned about scheme lists. And scheme lists are another type of linked lists, right? So we learned about regular lists and linked lists. And so if you remember Python's linked lists, they look a little like this in the bottom. I drew you a picture. Here's an example of a linked list, and this is what it looks like in scheme and in Python linked lists. So every linked list has two attributes. It has a first. First is like the element inside the linked list. So if you were to represent a list, this list as a linked list, you would draw it like we have below. And you have a first and a rest. And first is the element inside the list, and rest is a pointer to the next link. right? So rest will be another list. And it's first in rest in Python, but in Scheme, it's car and critter. And car gives you this. So car is like here, and critter is like here. And if you want to know how to create it, you can just do it like that. Or you can do it like that. Cons 1, cons 4, cons 9 nil. So there's a nice parallel here between Python and Scheme. All right, cool, we're getting warmed up. And when we're working with lists, I like to kind of make this like a handy cheat sheet for how to build lists out of the pieces that we have. So here's kind of an enumeration of that. If I give you, and by the way, for all of these, our goal is to get to this final goal of list of 1, 2, 3. So what functions do you use? If I give you a list and an element to connect to the front, then you should use cons. And almost always you're going to find yourself in this situation with one element and another list. And so you should almost always be using cons to solve these problems. But that's not always true. You might also have multiple different elements, like if you have 1, 2, 3, just single elements, all of them, then you would want to use a list to join them, and you can get to the same place by doing list. You could also get 2 lists. And by the way, in the problems we're solving today, we're actually going to need all 3 of these. So you should know how to do all of them. And if I give you these 2 lists, 1 and 2, 3, you can use append to link those up. Questions about this? Shouldn't that be quasi quotes for 2, 3? There should be a quote in front of that. Yeah, sorry. What if you have 3 lists? Well, you could do something like this, right? You could do append list 1, list 2. That gives you a list, right? And then you could also take that and you could append that onto list 3, right? So you can use a little creativity to link those all up. Good question. Any other questions? Is there a difference between list and cons? There is. Cons does this, list does this, right? We should do, I encourage you kind of just to think about it with like this definition, right? Here's what you use for this cases. Cons links up a single element to a list, and list links up multiple different elements. One good question is what happens if you, instead of doing cons here, what if you did list? List 1, 2, 3. What does this give you? Yeah, this gives you a nested list that looks a little like this, right? So if you wanted this list of 1 and 2, 3 inside, then maybe you would want to do something like that. But if you just want this list 1, 2, 3, then when you're connecting an element in a list, you should call cons. Let's see what else was happening. Cons always achieve what append does. Yeah, and in fact, append, if you look at the implementation, there's a discussion question on this. That question uses cons to implement them. Cool, other questions? By the way, if anyone would like to unmute and ask a question, feel free to. Thanks. I moved the pen circle. Does the cons turn the 2, 3 into elements? I'm not quite sure. Does the cons turn the 2, 3? I guess so when you call cons on 1 and quote 2, 3, what turns the, so what's actually happening here is 2, 3 looks like this, right? 2, 3 looks like a linked list of this. And what cons is doing is it's taking this 1, putting it inside a box and then linking it the beginning of the list, right? So the 2, 3 here, this whole piece of 2, 3 doesn't actually change in the process of calling cons. So even though it looks like maybe we broke up this set of list braces, this is just a representation, and under the covers, under the cover, we're just attaching a 1 on front. Yeah, and I'll leave the rest of the questions for Jamie to answer. But yeah, let's move on for now. And we'll see a couple of examples of how to use all of this in the problems below. Here's some general tips for solving these scheme problems that we'll be seeing today. Because we're working with lists in all of these, you should be drawing box and pointer diagrams to help you visualize the problem. Box and pointer diagrams, by the way, look like this, like these things. So in Scheme, there's no iteration. We have iteration in Python, but we don't have iteration in Scheme. So we'll always need to use recursion. And when you use recursion, remember always to think about, if you don't know where to start, ask yourself, what is the base case and what is the recursive call? And usually the base case is the easier of the two to figure out. And you can teach yourself at least a couple points just by asking yourself these questions, like what is the simplest case, the base case? Oftentimes the base case will be something like null, right? Null list. This is a great base case. Just to check, if we're working with lists, the simplest list is an empty list. And we'll see a couple examples of that. So when you're writing these recursive scheme functions, yeah, we talk about these base cases. You'll use some kind of con structure. When you recurse, maybe you want to call the recursion on the cutter of the list. That's a great way to break down the problem. And then I think this one's a really important tip, which is that when you write problems in Scheme, in my experience, almost all the exam problems I've seen on Scheme are not as hard as the Python problems. The difficulty comes from the fact that you're writing the answers in a really, really confusing language that is Scheme. And Scheme is pretty, especially when you first saw it, you're probably like, what is this language, right? It's just strange and maybe like still fairly new to you. So generally speaking, I think these Scheme problems are not as difficult as the Python problems you'll see on exams. And so it's easier if you write the problem in Python first, if you're confused, and then try to translate it over to Scheme. Okay. We talked about list. This one's a useful one. Null, this is a great one for doing base cases. Base cases. It depends. We talked about that as well. Any questions on this? If not, here's a quick poll. Would you like to work together in breakout rooms? Turns out my polling option actually worked. Poll. Democracy. Okay, everyone answered no. I don't need to wait for this democracy to happen. Everyone has voted and everyone voted no. Maybe you can see the share results. Now sharing poll results. All right. For the 9 people that voted yes, I appreciate your enthusiasm. Okay. So now Jamie is going to present to you a couple problems and we'll kind of introduce them to you, have you work on them, and then walk you through the answers. Cool, so I'll stop sharing here and Jamie can pick it up.
Yeah, let me just set it up really quickly. so we're gonna jump into some of the questions. Maybe take a look at this question, take a few minutes to try it out, and we can start going over it around 5:30. If you have questions, feel free to unmute yourself or use the chat. Okay, hopefully you got a chance to get started on this problem. We're gonna get right into it then. So first off, we know that it's going to give us a non-negative integer n, and we want to return the product of the digits. So using the hint, we want to use quotient and modulo somehow. And kind of the main idea behind this is we want to split between our base case and recursive case. So if we have a number such as 1, 2, 3, 4, 5, we don't necessarily know what the output is going to be right away. But if instead I have a single digit, such as 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0, then I can just return that by itself since it is going to be its own product. So the way I can split that up is by using an if statement. So I want to say if n is a single digit, so that's true if n is less than 10, then in that case, I want to just return itself. And otherwise, what I'll want to do is I can take off the last digit and I can call digit prod again on the remaining ones in order to get that product, and I'm going to multiply them together. So I want to multiply the last digit, which I can use modulo for that. So when I have modulo and 10, that just gives me the 5 here. And I want to multiply with the product of the remaining digits. So here I can use quotient, which is the same thing as dividing n by 10 in Python. So I'm using quotient instead of divide in this case because I don't want to have the extra floating digits. And then we can just end parentheses, prod, parentheses, and if. Okay, a lot of questions in the chat. So we do want to use modulo because it's defined as the same as percent as in Python, but in Scheme we call it modulo. For the base case, does n equals 0 and return 1 work? Yeah, I think that should be fine. For the base case, can you do equals modulo n 10 0? So if you have the base case where you're using modulo, where you have mod n 10 and you return 0, this doesn't necessarily get you what you want because, or so this is a bit of a tricky case. I think what would happen is if you have any product of 10, then it's fine. But if you have something like 12, eventually you're going to always hit 0. So you'll always be returning 0 rather than the actual number. Yeah. Can we use divide instead of quotient? You want to use quotient because divide will give you, for example, if I have quotient 10, 3, that will give me 3, for example. But if I had divide, that would give me 3.3333 and so on. Yes. Yes, someone mentioned that. Okay. Any questions if someone wants to unmute or also ask in the chat? Okay, if there are other questions, I think Albert will get to them. But otherwise, we can move on. So this is just the nicely written version of the solution. As we said before, another base case, multiple possible base cases. Another one is using quotient instead of n is less than 10. Okay, so moving on to the next question for contains. Here we want to take in a number num and a schemeless list. And here we just want to check if the number will be in the list or not in the list. So again, maybe take a few minutes, try this problem out on your own, and then we can start going over it. Also, feel free to keep using the chat or unmute yourself if you have more questions. Yeah, and I think as someone pointed out in the chat, if for the earlier problem, if you said if n is 0, return 1, that doesn't work because n is also allowed to be 0, in which case we want to return 0. So yes, good point. Yeah, so I can scroll back to the last problem, and what we have the base case here. Um, this is going to be the same kind of idea as where n is less than 10. So here we're just checking that if the quotient of 10 is equal to 0, that means n is going to be less than 10. Um, they're going to be equivalent. One question, will we have to consider cases where elements in the list in problem 2 are also lists themselves? I think it's fine to just consider it to be one list, no nested list. Okay, why don't we start going over contains? So again, we have some number, we have some list, and we want to check whether it's in the list or not. So first thing we want to see is whether we can access the list at all. So we can't do that if the list is null. Like we can't check the car cutter of the list because it will be null. So we want to say if it's null, then we know that this number cannot be in the list. So either we've traversed the whole list and it's not in there, or we were just given some null list by itself. And in that case, we just want to return false. Another thing we can do right away is, for example, let's say we were looking for 1 in the list 1, 2, 3, 4. Then we can just compare the car of the list to our number. And if we found it, then we're done. We know that the number is already in this list. So we say if the first element of our list, so car of list, is equal to num, then we found it, so we can return true. And our else case is going to be, let's say I am looking again for 3, and I realize I compare with 1, it's not going to be equal to 1. I want to keep going somehow, so I can just call contains, and I'm searching for the same number, so I want to keep num the same. But I've already checked the first element of list, so I can move along by calling cutter of list. And this will just tell me if it's in the rest of the list or not. So any questions on this so far? Okay. If you do have questions, feel free again to use the chat or mute yourself. But let's move on to the next question. Again, nicely formatted solution, which was what we covered. And yes, when we have quote 1, 2, 3, that will automatically denote a list. So the next question we have is add-ups, which might seem a little bit similar to what you've been implementing in the Scheme project. But now we want to do it in Scheme. Check out the doc tests here. They might be helpful in figuring out how we want to format it. So again, maybe take a few minutes and try this problem out, and then we can go over it. Okay, seems like people are ready to go over it. So why don't we get started? I think one thing to note in here is that we will be taking in an expression and we want to return a list. So that means even if we are given some number such as 1 or a symbol such as a, we want to return a list with that number. And if we have something like a nested expression, then we're going to get the flattened expression instead. So the way it's set up is that we have a few cases. First off, if it's null, if the expression has nothing inside, if it's an atom, such as 1 in this case, and if it's something else that's more complicated, such as these two cases. So in the first case, if it's null, we don't have anything that we really can do about it. So we just want to return an empty list, which in this case is nil. Also, we could use the quoted version of the empty list. For the other case, if it's an atom, we want to check if it's 1, 2, 3, some number, some symbol, or Boolean value again. We want to return it by itself, but we want to make a list out of it. So the way we can do that is by calling lists on our expression. And that will give us the form of something like this. Yeah. In this case, if you wanted to do return exp, that's fine because exp and nil are interchangeable. For what kind of values would atom value return true? In this case, we are considering numbers, symbol, Boolean values, but I would double check the villain procedure reference for that. Yeah, and kind of what people are getting at in the chat is the reasoning we have this list here is because later on we will be using it in append, which will start to make our lives easier. But continuing on with what we have so far. Okay, another question is if we had something like quote exp here. So what that does is the same thing as if we had quote, for example, plus 1, 2, 3. It's just going to return it as it is. It's not going to evaluate it. But in this case, we want to evaluate what exp is. So if exp is 1, we want to get 1 instead of exp. Okay, I'm going to continue on for the solution for now and then come back to questions, or Albert will take care of them in the chat. But for the case of append, what we want to do is that we have something more complicated now. So we can split it into two things. We can have the car of the expression and the cutter of the expression. So we know that the cutter of expression is going to be, the rest of the list. So for example, here it might be 2 and 3. We don't necessarily know what it is, so we want to apply atoms to it. And it's going to be in the same order, so it'll be at the end. So we pass in cutter of expression. But for car of expression, it might again be some nested lists, such as times 2, 3 inside our list in this test case. So in that case, we also want to apply atoms to it. And if it's the case where it's just an atom by itself, again, we're going to get a list, which allows us to just append them together. So here we'll be calling atoms again, but this time it will be on the car of our expression. Back to questions. Okay, so one question was for the second base case, we had to do thinking about doing something more complicated, such as splitting the car and the cutter of expression. In this case, because we know the expression is an atom, it's only going to be something like 1 or something like true. It's not going to be a list, so we don't need to call car or cutter of on it. We can just use list and combine it because it's just going to be a single value. Could we return con's expression nil for the atom case? Yes, that will do the same thing. What does atom question mark expression mean? All this means is it will return true if it's an atom, it will return false if it's not an atom. And in this case, what we're interested in for atoms is number of symbols, Boolean values. Yeah, I'll just write this out. You can also do con's expression nil. That's also fine. What if we had append map Adam's expression nil? Yeah, I think that should also be fine. I think so. Do we need to add? Sorry, I'm not too sure what the last two questions are referring, or the second to last question. Or are you saying, do we need to have this part or this part? We need to have this first part because no, I don't think there should be a quote anywhere. So this is not what we want because we'll be getting this in the corner. I don't think there should be a quote elsewhere. What exactly is a scheme expression? So a scheme expression is a list, and it can be a list of the form where it can be a single value. It could be something of the form plus 1, 2. And if we have the quote in here, then it becomes a list because we're not evaluating it as an expression. To confirm, so here, if you wrote quote exp, this will quote the actual word exp, but we want it, so it would give us something like this. But instead, we want something that evaluates what exp inside, so we can't necessarily do that. Does Atom exp check if the whole list has atoms? No. So, well, a little elaboration on atom.exp. Maybe I can share my other screen. So, from the, let me copy paste this in the chat. Okay, so what Atom does is it checks whether our single argument is going to be some kind of value, Boolean, number, string, or nil. In this case, since we're already checking for nil here, we don't have to worry about that. So it gives us the non-nil. It doesn't check if the argument, if expression here is a list, we don't actually have to, like it doesn't check within the list itself. Yeah, this does not work because we're not going to actually evaluate exp because it's already quoted. If things are quoted, we don't evaluate it. So here, we won't evaluate it to 2, 3. Yes, you would have to quote it and then unquote it. So like something like this. But I'm not sure if that is, if unquoting is in scope for this semester. Okay, I think that was most of the questions. Feel free to continue using the chat, but otherwise we will turn it over to, is it possible to use a map for the else case? Yes, I think someone earlier had a question about that. I think map is also fine. It would be something like, we would be mapping append to the rest of, to the expression. Yeah, and then we would want to combine it again. Yes, yes. Would changing append to cons work? So one thing that we might come across is we can't use cons here because of the case that carve expression might be some nested list. So what cons would do is that, for example, if I have cons of 1, 2, 3, 4. I'm going to get 1, 2, 3, 4, where this is nested, which is what we don't want. What append will do instead is that if I change this to append, it will combine the two lists without that extra nested version, because cons treats their first argument as a single element. Okay, feel free to continue using the chat, and I'll answer your questions in more detail, but I think we should turn it over to Albert so we have enough time for the rest of the questions. Yep. Okay, take it away.
All right. Oh, great. Thanks, Jamie. By the way, I think we're going in roughly in order increasing difficulty. If I had to guess the difficulty of these problems, I'm not quite sure. No one like maintains an index of which problems are harder and easier, and you may find them like some of them more tricky than other ones and not the same order, but we've tried to like ramp it up as we go on. So maybe I'll give you a little bit more time to solve these next two. By the way, the next three are deep reverse, insert, and directions. And some people have been asking, all of these are past exam problems. Probably the first two are maybe on the easier end, and these, by the way, weren't worth that many points on their respective exams. Digit, prod, and contain. These are pretty short questions, but they are actually all past exam problems. Okay, so I expect in the next, I guess, 34 minutes that we'll have time for insert and deep reverse, and probably not time for the last one, directions. If you want to try this one on your own, I just want to give you a little bit of fair warning. It is kind of confusing, so make sure you read the doc tests to figure out what's going on, I guess. So let's start off with deep reverse. And I don't remember which exam this was taken from, but I'm fairly sure this was taken from an exam. If not, it's a very classic problem in general. So there's no doc test, so I'll write some for you. Implement deep reverse, which takes a scheme list and reverses the entire list, all sublists, and kind of like infinitely deep reverses all of those. So for example, if I gave you a normal list like 1, 2, 3, deep reverse should return 3, 2, 1. 3, 2, this switch fold, okay. And I apologize in advance, my handwriting is not as good as Jamie's. Okay, so to reverse the whole list, but what if I gave you a list that's nested? So if I gave you a list like 1 with 2, 3 nested inside of here, not only is it going to reverse the order of these two things, it's going to switch this and this, it's also going to switch the order of, oh my gosh, this and this on the inside, right? So what you get as a result is going to be 3, 2 in a list and 1, right? So it switched the order of these outer lists and it switched the order of the elements within the inner lists as well. I guess helpful hint, you can use list, check if it's in a list, and then you can also use append here. Oh, we've seen a lot of append today. Oh, why did that? No, sorry. Thank you for catching my mistake. All right, how about I give you until, maybe I'll give you until maybe 6:05 to try this problem, and then we'll talk about it. This is a really classic problem. All right, let's talk about this. So, okay. So I think there's some recursion happening here. Does anyone want to take a shot at what some base cases might be, or what might be the base case?
No.
Yep, sounds like a good idea. Why? Because imagine if we're reversing a scheme list. The easiest list to reverse is just nothing, right? If you reverse the empty list, what should you get? I think you should get the same list back. And actually, I know this is a little bit weird. You use the word null here and you use the word nil here. Just the way scheme works, unfortunately. Okay, now we have this parallel structure. There's some kind of case here. It looks a little like this, right? If we have to write it out, there's some kind of case here. And then if this case is true, return append something, otherwise return append something else. Okay, so how do we think we want to split this? What are the two cases? They kind of run in parallel, apparently. Oh, perfect. Preeti says if car list is a list. Okay, what does that mean? So here's the strategy we're going to go about for doing this. We're going to go one element at a time and try to kind of move the elements to the end. Here's how it works, right? So if I gave you 1, 2, 3, what you would do is you would look at 1 first, then 2, then 3, and you would say, well, if we want to reverse all of these, basically what we want to do is we want to say, first, if we look at 1, then we're going to do 1 and then put the reverse of 2, 3 in front of that, reverse of 2, 3 in front of 1, right? And that is going to be 2, 1 and reverse of 3 in the front, 3 in the front. And then that is going to give me 3, 2, 1. So that's how we look at one element at a time. So one case for this would be, well, what if the first element is just a number or just a single atom? And in this case, I think it's going to be easier for us to check, well, is the first element of list a list or not? So if car list is a list. And if that's true, then we're not only going to need to move it to the end, but we're also going to need to reverse it first. So what did y'all do? Yeah, you could also use atom, I guess. Atom is kind of like the reverse of list. We just learned about that one. Cool. So what you said is, here's what Steve said. We should append. So here's an example. If we have a list, then that looks like this. 1, 2, 3. That might be let's try a better one. How about 1, 2, 3? Okay, the first thing that should happen in our list, that should go away, is we should put the 3 first. Right? That's like the cutter of the list. And then we should put the reverse of the car. Right? So first we want to take the cutter and reverse it. So deep reverse cutter of list. And then next, the rest of the list should be formed by taking the car and reversing it. So we want to deep reverse. Because we know the car is also a list, we can just call the same recursive function on the car. It seems like we're not done, are we? Because what happens if I just take, so here's the car. If I reverse it, I get 2, 1. If I take the cutter and I reverse it, I get 3. And what if I append these? I get 3, 2, 1. We wanted this, but we actually got this. So that's wrong. So instead, what we want to do is you want to take this and put it inside another list column. So this way, you have all of this nested correctly. All right, what about the other case? Well, the other case is pretty similar, right? Because what we did here for the case where the first element is a list is actually just a more complicated version of the regular one. If we have just a normal thing, like imagine I just gave you 1, 3, that's way easier. Oh, a lot of people are asking, why do we need the list? So when you take the car, so here, let's look at this list. An interesting thing happens when you pull out the car and the coder. So you pull out the car here, you get 1, 2. You pull out the coder here, you get 3. If you just take the parentheses at face value, you notice that actually we got an extra set of parentheses around 3, and we kind of had only the same set of parentheses here. And if you actually just connected these with the append, you would end up with, oh, I guess if you connected these with append, you would end up, after reversing them, let's reverse them first. Let's reverse them. This one becomes 2, 1, 2, becomes reversing, becomes 2, 1, and then 3. And if you connect these, this becomes 3, 2, 1. Right, so you ended up with basically one less set of parentheses around 1, 2. And if you want to add the set of parentheses back, then you should just call list on this whole thing, this whole 2, 1. And so now instead of having 2, 1, and 3, you have parentheses 2, 1, and 3. And when you append these, that gives you 2, 3, 2, 1, like that. Yeah. You can either think of it as you lost a set of parentheses, or you can think of it as just, yeah, you just look at like the case and what happens. You get 3, 2, 1. If you want to add an extra set of parentheses to get it to look like you want it to, then you can just call list on an extra. Right, if you're not super comfortable using the list function, you can also just use cons lst nil. Right, so another equivalent would be, instead of list, cons that thing and then nil. Basically, you would substitute this into here. Okay, for the parallel case, here's what happens, right? We want to append, we still want to do the deep reversing of the coder of list, right? Because coder is still a list, even if we have a so imagine this would be like 1, 2, 3. Okay. Right, for a case like this, you still want to reverse the coder of the list and put that in front. But yeah, for the car, and I think Steve has it right, for the car, because it's not a list, we don't really need to reverse it or do anything to it at all. All we need to do is just make sure that it's inside an extra set of list braces. And you can kind of check for yourself through doc tests that this works correctly. That you should end up with. So here's how it breaks up. It'll break up into these two, a list 1, a list 2, 3. We'll go through the reversing step. Sorry, we'll go through the reversing step. So this thing, deep reverse coder list, will turn 2, 3 into 3, 2, and then we'll append them together like this. We'll get 3, 2, and then you'll want to add this extra set of parentheses around 1, like so. So 1, 2, 3, reverse it to get 1, 3, 2, and then when you append them, you want to call list here to get an extra set of parentheses around. Oh, no. Sorry, not, wait. I messed this up. Let me try this again. You don't want an extra set of parentheses here, but what you want to do is you want to make sure that because car list is a single element, append only takes in 2 lists. So you want to make sure the second thing is actually a list by calling this list function. Sorry. There's no extra set of parentheses here, but you need to make sure that this is a list. So makes sure that car list is a list. And that's for the append function to work. So if we use list for both car lists, so it allows us to use append. Yeah, exactly. Thanks, Jackie. That's probably a better explanation than mine. And can't depend on the, yeah, so this is why I made this little slide. I think this really helps because append and scheme and append in Python are totally different. And it's like, I feel like it's super confusing, right? Append, when we learned append in Python, append was a function as opposed to extend that only added one element. And that was like the part that made it unique is that it adds a single element. In scheme, append is kind of like Python's concatenate. So it's a little like the plus function that we use for two lists, right? LST1 plus LST2. That's scheme append. I agree that it's very, very confusing. However, if Preeti asks, however, the second line of the second case already returns a list, won't using list produce a second, produce a nested list? It can't, because in this case, we know basically this is like the atom case. This is like if, imagine like the else basically means if car list is an atom, right? That's like what this else means. So that means that we'll always end up with, as the car of the list, we'll end up with something like this, right? Like 1, just like a number, a Boolean, a symbol. And to be able to use append on that, we're going to need to call list on it first. Because append takes in two lists, right? It basically connects two linked lists. So we want to make sure that this element is actually inside of a linked list. Okay. Any other questions? Seems like Jamie answered one of these questions. I thought the else case takes care of that and ensures that it's a list. Yeah, exactly. So that's why. No, sorry. This one takes care of the list, right? This is the list case, and then this is the atom case. And then if it's an atom, we need to make sure that we call list on it to make it into a list. Yeah. So I don't know. I'm just trying to explain, I guess, why we call list on this thing, and that's what makes it into a list. Yeah, if it doesn't make sense, hopefully Jamie can clarify. Let's keep going on to insert. So what's insert? Insert says, and let's walk through some doc tests for this as well. So here's what a group is. We have this notion of a group. Let's see, it's this sentence. So a group is a list that begins with a key followed by values. So here's a group. A group might be like this. You can imagine a group of kind of like an entry of like a dictionary in Python. So you have a key, let's say like our key is 5, and then we have a set of values. Say, for example, 1, 2, 3. That's one group. And the key 5 is linked to the values of 1, 2, 3. And here maybe is another group. You could have a key of 10 and then link it to some elements like 5, 6. And then here's what this function is going to take in. It's going to take in a list of groups. So basically, here's an example of a list of 2 groups. Each of them has keys and values. And then I'm going to ask you to write this function insert that we pass in a list of groups like this. And insert is going to insert a new key into the group that's started by, or new value into the group that is started by key. So for example, if I insert, if I say key equals 5, and then value equals, let's say 11, we're going to go through this list of groups, group 1, group 2, and figure out which one has this key. And if it has the key, we're going to put in value as the first, put in this value into here. So right, this will go in as this element. And for most cases, this is going to be normal and it's going to work like this. But if we were to look at a case where P is not in either of these groups or however many groups there are, then what you're going to do is you're going to create a new group at the end. So let me draw a scenario of this. How about like this? Copy this whole thing. Copy, paste. So for example, what if I was trying to add in key equals like a new key. So we don't have, let's say this key 6, and we want to add in another same value 11, then because we don't have any groups that start with the key 6, what you would do is you would insert a new group. Let's go away. A new group down here of 6 and 11. So 6 and 11, and you would add this at the end. Can multiple groups contain key? I think let's just work with this. Let's say assume all keys are distinct. I don't know if it says this elsewhere, but you can just assume that. Cool. So take about, let's say, 5 minutes to work on this. One tricky part of this is probably going to be that you're going to need to insert this value kind of in the middle here. So you need to think about, how do I break open the list and kind of build a new list with 11 in between the first and the second element of this group. Pretty tricky. Okay. This one's pretty tricky. Let's take a shot at it. So we have two nested ifs, and this is kind of like, sometimes you'll see the structure. It's a little bit strange, I guess. But some people like the structure more. You can think of it basically as there's three cases here, right? There's one case in this first blank, one case in the second blank. Sorry, there's one case in the first blank, there's one case here, right? So there's one case here, and then another case here, and then another case here. So, well, we know there's a base case going on somewhere here. Does someone want to take a shot at what the base case is? Yeah, well, something should be null. And you know, I guess it's like, if you're thinking about what is the base case here, you should think about what is the procedure to go through to figure out where to insert it, right? So if I gave you a list of groups, what you're doing is you're going to want to walk through the groups, like maybe like iterate through the groups one at a time. So you look at first this group with 5, right? This one right here, this group. And then you'll see, is the key inside here? Then you'll look inside the next one and see, is the key inside here? And you'll stop whenever you find the key. And that means that when you go through all the groups, and if you didn't find anything, that means that groups is going to be null. So if null groups. Okay, what do we do if groups is null? Do we just return nil? Yeah, so we're supposed to return this, right? We're supposed to return this thing, this 6, like here, 611, right? You're essentially returning a list that looks like that. So how do we do that? Some people, yeah, and I think the one that's right looks like Sally's answer. Some of these, you can't do some of these. So you cannot do something like cons key value. This is very, very close. But the problem is this thing is not a list. And so this will error, right? Value is probably just going to be a number. So what you'll need to do, if you want to do this, is you could do cons key, cons value nil. That's one way to do it. Here's another alternative. You could do this list. Oh my God, I keep switching to this crayon. Shouldn't slides know I don't want to use crayons? Okay, list key value. That will give you this thing. It will give you this 611. And then you can call list on it again. So that's basically the two ways to build this. You can also probably mix up like the cons and the lists to make some sort of Frankenstein in the middle. But both of these are valid strategies to get the base case of like this thing, 611. So this takes care of the case of if key is not in groups, whatever, right? That takes care of that case. Oh, I think you need another, yeah, you're right. Some people told me this. This thing should be, if you want to use only cons, you could do it like this. You could take this and cons it onto nil, right? And that is the complete one. Sorry. Why do we need double lists? Yeah, because we're supposed to return so we're asked not to return a single group. If we returned this thing, 611, that would be returning a single group. We're supposed to return a list of groups. So in the case of like, imagine if I passed you in this list of groups, that's like no groups. And then when we're returning, we want to return a list of the one group that we just created. It's like a list of a list. Okay. What about in the other case? So what is the non-base cases? What are the recursive call cases? So we have this equal thing here. What are we trying to check? What is this equal thing checking? key car groups. Okay, what does that mean? What does that mean? Okay, so as we said earlier, basically what we're gonna do in this problem is we're gonna walk through all the groups and check. We're gonna go through all the groups until we find the key. So we're looking for this key, like imagine we're looking for this key 5. That's weird. We're looking for this key 5. What we're gonna do is we're gonna go through all the groups until we find 5. And if we find it in the group, then we're gonna stop and insert it. So how do we do that? Well, one way is to check if we find the key in the first group. And we do that by seeing if key is equal to car groups. Why car groups? Well, car groups is because what is car groups? Car groups just gives you the first group. So that will give you this thing, this whole first group. Car groups gives you the first element of that group, like the key of that group. And you want to check if that is the key you're looking for. Okay, if it's the key you're looking for, what do you do? We're a little short on time, so if someone just wants to give me the answer, I'll like just write it down and explain it in brief. Let's see. So for the first part, you took, let's see, I'm gonna use, I'm not quite sure about the list one. That might be right, but I think I've seen the cons one, so I'll take a shot at this one. So you want to take, you want a cons on key. So that is, well, you don't want a cons on key, do you? You want a cons on the first thing here, which is going to be car groups. That is the original key. Oh, actually, you're right. We can use key, right? Key is if it's equal, then we can just use key. Never mind. So cons key. Cons key. Attach that to the value, the new value that you're inserting, and then you want to attach all of that to, I'm going to run out of space, cutter of car of groups. And cutter of car of groups, by the way, is this thing, right? This 1, 2, 3 in the list. So if you split up the car and cutter, this is the car and car groups, and this is the car, this is the cutter car groups, and you kind of want to put value in the middle. And then you take all of that and depend it onto insert key value. So I don't want to write this, so I'll show it to you in the solution. So these are the two parts. You want to take this thing and append it onto the original rest of the groups. So the original rest of the groups is cutter groups. Basically what you're doing, this whole thing just says, take the original key and the original rest of the group and put value in the middle. Otherwise, so what if you didn't find the group here? What if, for example, you're looking at something where the first group is not 5? Then what you want to do is you just want to take the first group and depend it onto, take the first group, this is the first group, and depend it onto what happens when you try to insert into the rest of the groups. And that's by calling insert on recursively on the cutter. Yeah, probably don't use two double AR groups. Yeah, I'm not sure if those are defined. I wouldn't use this. Ruthie asks, why do we make a list with the current car of groups and then make a recursive call? Oh, yes. So whenever you do a recursive call, so what happens if you just call insert on the clear of groups. So I guess we're looking at this case and we're saying, why do we have this car groups in front? So imagine I have, I'm inserting key equals 5 and value equals 11, but I have a list like 1, 2, and then 3, 4. So these are my keys, 1, 1, and let's make this 5. So how am I going to insert this? Since I know it's not, the first element is not 5, the first group is not 5, then you actually want to break it down and insert into the cutter. So the cutter is this. The cutter is list of 5, 4, that group. And when you insert into here, you're going to get 5, 11, 4. That's great. But what you want to return actually is all of the groups, right? This is just the cutter. This is just the rest of the groups. You actually want to keep the 1, 2 as well. So you want to add in the 1, 2 into here. And that's going to give you 1, 2, 5, 11, 4. So you're going to need to con that on to the beginning. Claire asks, why is the first value not cons before the key in the second to last line? The second to last line is here. So why do we not cons before the, oh, why do you put this value after the key? Yeah, because I guess if you look at this example here, you want to put, you want the key to always go first in the group, and you want to insert value added to the beginning of the group. And I know this wording is kind of confusing, but hopefully the doc clarifies that the beginning of the group is just after the first element, or after the key, that is. Lily asks, can you explain why cons key, cons value, critter car group, so this second to last line right here, why this doesn't lead to a nested list? Yeah, so whenever you see this thing, right, cons 1, cons 2, cons 3, or cons rest, like rest is some list, right? So this always is going to create a regular non-nested list. In fact, whenever you see these like sequences of cons and if there's no like list functions in the middle, this kind of thing is going to lead to 1, 2, 3, right? Like 1, 2, whatever rest is. Imagine rest is like another linked list. Rest is another linked list, then it will lead to something like, I don't know, 4, 5, 6, whatever, 4, 5. This will create a regular linked list. And that's the same structure you see here, right? Key, cons value, these are both numbers. And then this thing, critter car groups, is just another list. So you're consing on key and value to the beginning, and this will create a regular list. If you saw something like, if you replace one of these cons with, for example, list, or if you replaced, or if you put, for example, another cons in the front here, then that would create a nested list. Gosh, lots of questions. We've done append list key value critter car groups for the first cons blank. I'm thinking you can. Does this fit inside the skeleton, I guess, with the cons? The first cons blank. I think this will work. Yeah, I think you can also have an append solution. I didn't look too closely at this, but I think so. Cons can take 2 lists. Yeah, cons can take 2 lists. It'll just form like a nested structure. And I guess if that's what you want, then that works fine. In this problem, yeah, it seems it's the first element is a list, and that creates kind of a nested, like the group structure here, the nested group structure. Yeah, I'll keep answering questions. If you want to go, this is pretty much all we're going to do for today. thank you for coming. Best of luck on finals. We have some nice little comics for you. You got this. Do you have any final advice, Jamie?
I guess don't forget to take a break once in a while. We're very close to the end of semester, so you deserve it. Best of luck.
Cool. Yeah. Good luck. Thank you for coming today. I'll answer the last questions that are remaining here. I know this one was pretty tricky. Okay, my AirPods keep dying, so I had to switch headphones. That's all the content for today. I'm going to stop